Okay, I am Troy Tittlemeyer, the CEO of MagmaChem Research Institute. I left the oil and gas industry at the end of 2019 with the opportunity to work with Stan Keith and work with MagmaChem. And it was an incredible journey since day one, as some of you can imagine, working with Stan every day and getting to understand the depth of MagmaChem and the history of MagmaChem. And I'm very honored to be here today. And I want to say on behalf of MagmaChem, thank you to the Arizona Geological Society for allowing us the opportunity to speak to all the members, the people of the society. It's so important to keep us together as geoscientists, and it couldn't exist without everybody here, even the one that can't figure out how to mute their microphone. It allows us to collaborate. It allows us to ask questions, and it allows us the opportunity to really share these ideas. And tonight, specifically, is sharing the ideas that came about 3 years of research from Dr. Jan Rasmussen and Stan Keith as they were asked to contribute to what we believe will be a major contribution, not to just Arizona geology, but to geology as a whole. The work for this 4th edition of the Mineralogy of Arizona is absolutely incredible. The details are incredible. So we're going to get through this. Jan Rasmussen, her point for this presentation was that she wants everyone to know that the magma metal series classification, the colors that you're going to see of these polygons in the map across the whole state of Arizona, these colors are empirically built, and they're backed by a lot of research, and it's incredible the amount of details that go into that. She's going to talk about that and teach us. So that's the important part with that. She's an amazing researcher, and she's a teacher, and she's going to teach us about the magma metal series and how we can use it as a viable tool as geoscientists to de-risk our exploration efforts, to de-risk our time and attention on the project. Stan Keith, in this 3-year journey, he saw all these economically potentiable mineral systems that not a lot of folks talk about. And he said, there's a lot of potential in the state of Arizona. Arizona is, for several reasons, is an exciting place for metal exploration in our future, and certainly in the next 5 to 10 years. You would argue we could be going into a bull market for the metals industry. That's huge. Arizona is favorable to metal exploration. Arizona should be looked at very seriously and very carefully, the geology and the opportunities we have in this state to take on the responsibility of controlling and allowing us to explore for the natural resources that our country is relying on. So this is an exciting talk. Again, it's an honor to share this time with you, and thank you again to the Arizona Geological Society for this opportunity. And I think this talk is going to be really fun. We look forward to the discussions at the end. Dr. Jan Rasmussen, the floor is yours.
Thank you. I was asked about 3 or 4 years ago by Ray Grant to write about the geologic history of Arizona and prepare the mineral district maps so that mineral collectors could easily use the maps to find their samples they like. So the former edition, the 3rd edition of Mineralogy of Arizona, was done in 1995, and Ray Grant was one of the authors. So he's the principal author of our 4th edition. So Ron Gibbs, Harvey Jong, myself, and Stan Keith are the other co-authors. And the U of A Press will publish this in late 2021 or 2022. So we're still talking about the cover, but that gives you an idea. So the previous map of mineral districts was done in 1983 at the Arizona Geological Survey, and it had sort of a non-predictive kind of schedule of mineral types. So it was not real specific on the kinds of deposits that you could find. So we wanted to use the magma metal series that Stan has developed over the last 30, 40 years to help people de-risk their exploration. So one of the things that we want to emphasize is that mining districts of the past are different from what we're calling mineral districts. So the mineral districts are based on the geology and the type of metals, the source of magmas, the date, the million years ago that the deposit was formed, and so forth, so that that's different from the old mining districts. So here you see the former one with the sort of blobs. There are fairly good location information, but it was really hard to use the colors to help you find where particular minerals would be. So that was our goal. So this is going to be the new mineral district map, and all the maps are done. John Callahan has turned them into pretty, added the roads and the topography so that you can locate yourself. So we have improved the quality from the third edition, which was just blob maps, to the present one, which is very specific on the type of metals like porphyry coppers, or the types of age dates and metals that would occur there. So in this presentation and in the book, we have subdivided them according to what are called the magma metal series. So we've got these hot colors of reds and yellows are the metaluminous ones, and the cool colors of the blues are the peraluminous types. And the peraluminous types are basically two mica granites, both muscovite and biotite, in the associated igneous rocks. So these peraluminous ones are crustal melt. The metaluminous ones are sourced in the magma. So those colors are standard throughout this presentation. So in the example here, the yellow refers to porphyry coppers. The blues here represent tungsten or copper gold systems. And what we've noticed as we put these maps together is that there are what we call super systems. In other words, a large area where you have the same kind of ore deposit, same age, same metals, so forth. So the concept for mineral collectors and for mineral exploration people is anywhere in this super system might be a good place to find similar minerals or similar ore deposits. So sort of stay in elephant country when you're looking for elephants. So that basic classification of peraluminous and metaluminous subdivides the types according to this variation diagram. And all of these definitions are described in more detail in all of the publications that Stan and I have done over the last, and Monty Swan have done over the last, say, 30, 40 years, one of which was in an Arizona Geological Society publication. So if you're a member, you can easily go and download those. So the peraluminous or two mica granite ones can be deciphered based on a variation diagram of the whole rock geochemistry with strontium on the y-axis and weight % of calcium oxide on the x-axis. So you get your whole rock analysis of the rock, the igneous rock that's associated with it, and plot it on this plot and find out whether it's alkali-calcic, whether it is calc-alkalic, in which case it would probably be a tungsten deposit, or if it is peraluminous calcic, in which case it would be a gold deposit. So many times we do not have these detailed geochemical analyses. So what we use instead are the minerals. So if you've got both biotite and muscovite, if there's a presence of garnet, tourmaline, pegmatites, aplites, so on, then you would be in this peraluminous part of the diagram. So in terms of plate tectonics, you get these peraluminous deposits when you have flat subduction or when you have continent-continent collision. In Arizona, we found all the peraluminous ones are associated with flat subduction. And there was one of these flat subduction episodes at the end of every one of the 14 or so orogenies that have affected Arizona. Now, if you're in the lower part of this diagram, that's metaluminous, and that would be where you have minerals such as hornblende, any amphiboles, pyroxenes, olivines, so on. So in the case of the metaluminous, the way you find out which class it is with this diagram, which has K2O whole rock versus SiO2 in the whole rock. So for example, if you plot the K2O versus SiO2 and you end up in this yellow area, then you have calcalcalic and you are likely to have a porphyry copper deposit. If you end up in this alkali calcic zone, the orange zone, then you may have copper in your analyses, but it will not be economic for copper. It might be economic for zinc, silver, or lead. So this diagram is how you determine which of these classes you would be in. And the way that those are caused is from where the melting occurs in the subducting zone. So if the melting has occurred down here, this is the gold copper zone, or the MQA, the quartz alkalic zone. So if you have melting in the orange zone here, that is the alkali calcic source, and that would give you lead, zinc, and silver. Similarly, if the melting is occurring in this part of the slab, then you're going to possibly have porphyry copper deposits in this yellow here. So the orogenies that have gone through Arizona since the last 2 billion years, most of them have had a subducting zone that has become shallower with time. So as the zones of melting get shallower, you have the types of ore deposits on top of each other. So you may have, say, quartz alkalic copper gold like Bisbee, and then later it might be the similar crust might be intruded by the alkali calcic or lead zinc silver things such as at Cortland. So eventually you get a very big complex mixture of ore deposit types. So Stan and I had great fun doing the detective work of figuring out these various classes for all the different mineral systems. So another thing that we noted on the map was the oxidation state of the associated pluton. So, for example, most of Arizona is this pink in the map.
So
and
am I.
Pink
I see
here
you.
Is the oxidized material. And the oxidized material.
I hope this is really helpful. It's really critical. Take notes and ask me questions afterward.
This crust would have influenced the material that came up through it. Most of the crust in Arizona is probably underlain by ruined granite, oracle granite. The 1.4 granites of the Picaris orogeny. The oxidized crust has an influence on the fluids from the magma that is coming up. For example, if the crust is oxidized, then when the fluids come up, the gold in the fluids goes into the rock-forming minerals. And the mineralizing fluids then are base metal rich, copper and possibly lead zinc. So that is a refinement of the other classes. But it's important for mineral deposits because if you have this reduced crust, the blue, for example, here, then you are likely to have more gold-rich materials or even oil, for example, because in that case, the gold does not, the base metals go into the rock-forming minerals, and the gold then goes out into the mineralizing solutions. So the oxidation state is another important feature. Now, when you're doing exploration, you can follow this decision tree. Again, the blues are the Peraluminous, and the warmer colors are the Metaluminous. So you would do your whole rock chemistry of the associated igneous rock. You would figure out the aluminum content and the alkalinity, which are on the maps, and you would follow down through this decision tree until you get to the part that is the fractional differentiation. And that is this diagram. And I don't expect you to see or recognize all these minerals, but the concept here is that you have a pluton that is fractionating, and as there is some kind of a release of structure, some kind of movement on a fault or something, then part of the material will solidify and emit or send out a hydrothermal fluid. Then the part of the rock or the magma that is still liquid will move a little bit depending on where the cracks are, and you'll get another release of fluid. So this is what we call stage 2, and it is related more to the iron-rich part and the propylitic alteration. Then the stage 3 release is the part that is economic. In this case, this is a porphyry copper or metaluminous calcalcalic. You can have one of these differentiation diagrams for each one of the classes. But when you are in a series of fluid releases for the economic portion of the porphyry copper system, you want the stage 3. That's where the chalcopyrite, the molybdenum, and so on is. A later release would be, say, the breccia pipes, the moly, quartz feldspar, and so on. So this is something that we put on the maps as stages only for the porphyry copper systems. So on our maps, we designated that with numbers. So this, for example, is in Mojave County, the Hualapai district north of Kingman. And you see all these different districts that we subdivided it into. When you analyze it for the particular stage, we have stage 3 and 4 in this version here. So for example, the Ithaca Peak, the place where the Mineral Park deposit is, that is a stage 3. The stage 4s are slightly later and more peripheral, and those have more either lead zinc or precious metals. So only for the porphyry coppers have we had this much detail. When we went through these districts, we found what we call a parade of orogenies. And each of the orogenies had a similar kind of sequence. So in the Precambrian, we had orogenic belts or mountain building belts added to the craton, the core of the continent, in a direction towards the southeast. So this map shows the southeasternmost edge, for example, of the Yavapai orogeny. So most of Arizona has a lot of Yavapai orogeny rocks, particularly in Yavapai County. Then the Picaris orogeny is the 1.4 granites, and like the Ruin granite and the Oracle granite, this is the southeasternmost edge, but there are plutons of Picaris orogeny all through all of the previous orogenic belts. So most of Arizona's really deep crust is this Picaris orogeny, which is why so much of it is oxidized. When we looked through this parade of orogeny, we noticed that there were 3 phases to each orogeny. So the primary, or the first one, is the metaluminous, where you have a shallower slab, and then peraluminous, which is the flat subduction, and then the when the crust is really high, then you have erosion and supergene alteration and rifting and serpentine-related mud volcanoes. So here are the 14 or so orogenies, a few more if you add all these in the Paleozoic. And you'll notice that this same sequence of the yellows and blues, yellows, oranges to blues, occurs in each one of these sequences. So you can get a different type of ore deposit in almost any one of these sequences. So we're not going to talk about all of them. You can look at this on our website, the Magma Chem Research Institute website, or on the AGS website, and look at this in more detail. So one of the other things that became obvious was the intervals between the orogenies was when all the really pretty minerals were so obvious, and that was during these reorganization events. So Stan now is going to talk about the four out of the 10 different prospective places to look for ore deposits. So Troy, are you ready?
Okay, if everybody can mute their microphones, just one last reminder. Stan, the floor is yours.
Okay, the floor is really 2 people right now. There, you notice that I like lizards. So my mascot, which is doing the real thinking, is sitting on the modified dollhouse. And I'm buried in all, this is typical work stuff here that involves all the various things we did to put together the mineral systems, which are quite different from the original map. And I might say that the one thing I think that was really important about the original map was that was the first time anybody had ever tried to draw a fence line around mineralization of a specific age and presume magma associated and ultimately magma series metal type. In the case of the Arizona exploration potential that came out of this, we had four, well, ultimately 10, and there's probably more, but we're only going to talk about 4 of them. Laramide gold, and that's associated with the Peraluminous calcic. These are typically sodium-rich granites, really white granites, associated with flat subduction. And then we're going to talk about the Jurassic porphyries and a major new cluster of these things that have shown up in western Arizona that were originally thought to be mid-tertiary, but they're not. Talk more about that in terms of the dating information in a bit. And then we'll return to the old classic Precambrian volcanogene massive sulfide. There's still plenty of legs in those guys. And of course, our old favorite, the laramide, porphyry, copper, silver, molybdenum systems. And I might say that in the skarn environments for the Jurassic, we could almost add rhenium to that. That's another thing that's going to emerge as a possible thing. Put that in your airplanes. So we have the magma metal series, again, to reiterate, is an empirically based correlation of magma chemistry and metal associations linked in space and time. And that's a repeatable, specific, and again, source-based. That's what gives it its predictive power. Okay, next. The idea is this is from a mineral collecting point of view. This is from an explorationist point of view. It would reduce exploration risk in a sequence regional to drill hole scale. That was sort of what that decision tree was telling you. And then when you get into a sequence, we typically find there's a geography to it that goes from mafic to intermediate to felsic, with different fluid releases coming on along the way related to structure and depressurizations that tie into kinematic events going on that structure. In this case, right slip, strike slip. And strike slip faulting is just really emerged in all of this. So that's the Pluton vectoring, and then you could do element dispersion analysis to look at the zoning of the actual fluid systems that come off. Better get a good mapper on board to do kinematic structural analysis with detailed geologic mapping. I used to do that. And what we're really kind of doing here is regional tectonic and metallogenic analysis with that mineral system map that we've been talking about. Next. So again, I want to emphasize this sort of restates things. The low pressure structural sites. This is the New Cornelia pit at Ajo, and we're bringing in a series from a diorite over here to the west through to a hornblende granite, biotite granodiorite, and then in the southeast part of the pit, we go into a biotite granodiorite, which is actually associated with a lot of copper mineralization that they never did finish mining, and that there's a lot, the vectoring says there's a lot of potential out under this sign. Okay. Again, just to emphasize, people have thought that this is where you go for porphyry coppers, but there's only two epochs where you have what people would call real porphyries. One is in the early Jurassic, and we'll talk about that western Arizona province in a minute, and the other one is in the Laramide, which is in the basically the late Cretaceous Paleocene. And all the rest of these are something else, and yet a lot of people have looked at copper occurrences in these, tried to force them into one of these two guys without success. A lot of money's been spent errantly. Okay, next. So now we'll look at the Peraluminous calcics. Now, that's something that people looking for copper need to understand, is that in Arizona, you'll get a little copper occurrences, but these are fundamentally gold. So Copperstone is not a copper mine, it's a gold mine. And there are Peraluminous granites there, despite what some people might want to say. And we think it's going to be the same age as mesquite, which is well known. Fortuna is an old historical producer, but the really big one is this Herradura thing. They're north of 10 million ounces just in resource right now. Probably several million just came out of this pit. It's the first pit. And the first actual open pit was the Mesquite mine down here, but we're sort of in a Peraluminous gold belt here. And we've built tables and we have extensive spreadsheets on every polygon that's on the map, including these guys. Just some pretty minerals. Take a break. Look at wolfenite. Here, wolfenite's just not a collector mineral. It's a exploration guide at Herradura for gold. So whenever they see a little pocket of wolfenite in the Herradura open pit, they get excited because they can expect that they're going to be close to a pretty high-grade gold occurrences in the pit. This gets back at the flat subduction and the idea that when you see a peraluminous granite, that is telling you you had flat subduction. And not enough of that gets said around here. Everybody focuses on the plutons that lead to porphyries, but by far the most important things volume-wise in the laramide, for example, are these peraluminous granites. And they form the guts of the metamorphic core complexes. And when you see one, you can bet Dan 10 six-packs that we've had flat subduction around here. And he won't take the bet, because he knows what I'm talking about. Is that, in fact, looking at one at Vulture. Jurassic. Let's have a look. Okay, there's your familiar lavender pit. Now fading into history. But the new history in Western for Jurassic porphyries may be in Western Arizona at a place called Yuma King and several of these other ones that might be expandable. But I'm going to focus on Yuma King because I know that one pretty well. Let's go to the next one. That's just some Bisbee stuff. And it's this cluster out here near Parker, Arizona.
Oh, you know.
And in particular, we're going to look at this one here at Yuma King down at the southern end of this thing. This is quartz alkali. We're in the pink colors. And we know that. We have a lot of petrochemistry at this one, Yuma King. There is an oxide resource at Yuma King, and you can see how the oxide things are replacing folded stuff that's been through the thrusting event. So these things are much older than any detachment event, but we have direct radiometrics, which we'll look at on this in a minute. There's a turquoise occurrence there, that spiderweb turquoise, that potentially could get dug up. It's right in here. You could almost potentially put a small pit in here and possibly start digging turquoise. Next. Here's another bubble diagram, as I like to call them, which is a fractionation chart for quartz alkalic. This is different, similar in style, but when you look in the gory details, you'll see different minerals in here appearing at different times in the hydrothermal fractionation sequence. And right now we're going to look at some stage 4 and 3 stuff. So here's the stage 3, and this is copper, gold, molybdenum, and we could add rhenium to it, which we do here. As per, this is an example, one of the higher grades where we had 1.868% copper, 363 ppm moly, 370 ppm rhenium. That's a big deal. 220 ppb gold. Good byproduct, and 19 silver. Good byproducts. But there's we got a lot of big rhenium numbers throughout, up to 0.5% rhenium in the skarn environment, which I might say from talking to Rich Lavelle, that's same thing going on at Bingham, Utah. So this is a Bingham, Utah analog. Here we are looking at folded chalcopyrite-magnetite skarns. And here's our stage 4, elastitic haplogranite, which intrudes biotite quartz monzonites. Lots of moly in these core boxes. You can look at it easier, some nice assays. And we dated rhenium osmium, courtesy of Jonathan Boswell of Anglo-American. Don't know if he's there now anymore, but luckily we got enough. They came in, collected some of this, and we got 190.6 million year age on the molybdenite, putting it in the Bisbee time epoch. And this has strong geologic analogy with those other things that we were looking at. Next, which are these guys. So Planet, Mineral Hill, Cienega, possibly Cabrala. All of these things potentially are expandable. I really like Planet and Mineral Hill. Well, of course I like Yuma King. And by the way, get it back there. There is a gold play that I saw John Mark screwing up with our talk. And that's right out in here. And that's for gold at about 160 million. And I don't know whether that's a Jurassic. It's possible it's associated with a Peraluminous set of plutons, but I'm still trying to scratch my head on that. Next. Okay, so now we'll just go through the volcanogene guys real quick. This is our map of the Agua Fria belt, which has Jerome at one end, which is a big, massive sulfide. 30 million tons, and a similar one that's growing at K. They're adding more drill holes to it as we speak. I heard that it might be north of 6 million tons, and it's probably expandable. I don't know, maybe up to 10 million, but it's something that a historical thing that Exxon expanded into several million tons, and it's continuously being expanded. Talk to Dan Lux a little bit more about that. Up here in Yavapai, or Mojave County, we have the Antler mine, which is actively being explored, and I think they're adding tons there. And I think the Pinafore has some holes in some good copper zinc ore, and that's expandable, and that's kind of an extension of the old Dick massive sulfide belt south of Baghdad. Just a little bit more, just showing where K is and just giving you a sense of the texture of these maps that we've put together. For example, there's some laramide overprint in the Ticonderoga plutons. So there's all kinds of different ages. This is a classic example of how you've had all kinds of different things mixing around. That is a product of all of this parade of orogenies and parade of overprints. And you can sort them out using the magma metal series approach. And here, of course, is the classic at Jerome. No more needs to be said there. Next. Just giving you a little idea how these formed. This is fractionation from a rhyolitic magma source. Probably had black smokers, but not submarine black smokers, arc black smokers. This happens to be a modern seafloor black smoker from 21 degrees north, I think. Next. Now we'll take a look at our porphyries. And these are porphyry copper plays brownfields. That's why the brown circles. These are also include recent discoveries. So it's kind of a semantical switch up as to how you want to play this game. But of course, the most recent one is the resolution. And I think there's good play north of the currently known resolution under Oak Flat. It goes right up to it, and it's going to keep going. That's going to be good brownfields play, possibly deep resolution. Cholito southeast if you're down near Hayden. Christmas west underneath the old classical Martin Formation replacement ore bodies in the O'Carroll bed. This is a diabase play, and they need to drill that hole. I keep bugging them to do that. They haven't done it yet. And these other ones we'll worry about later. And we'll take a look at the Greenfields play here real quick at Troy Ranch. I think we're out of sequence here. Keep going. Oh, yeah, okay. So these are stage 4s. These are the veins. This is a magma vein, mine. I saw Scott Mansky. It's funny because, I've been convincing on, everybody's been convincing on it, and they all know, there's got to be some big thing out to the east. Well, I got there my own way. This is a stage 4 vein. And in terms of looking at how its metal zoning went, it said there's got to be something out to the east and possibly to the south. And you got to go get it. And of course, eventually they did. Scott Mansky was part of the discovery team. Okay, so here's the, God, you just love to have that clicker. It's got control over me. This is a good example of magma of liquid fractionation. That's what happens in these things, is you get because these are really hydrous magmas, you get a density-driven fractionation. So the high-density stuff fractionates, and it creates its own magma bubbles, which you can see have frozen against a lighter matrix here. So the lighter matrix, which is lower density, it moves on, and the darker stuff, which is in this case it's sort of hornblende biotite granodiorite, stays behind. And the white stuff moves on, and then this stuff will release this event, which is the stage 3. So, but this then is a different kind of fractionation. So, but if we look at this, we see how we have the dark crystals and the lighter crystals, especially on this one, this ocular guy. And that's crystal liquid fractionation as opposed to liquid fractionation that we were looking at. And then these other types are high. Once you get the hydrothermal release, that's hydrothermal fractionation. Anyway, so we're going to take a look at a couple of these applied to the Troy Ranch guy. And the ones you most want to pay attention to are these orange guys. That's our stage 3s. We got a lot of it right here, and it goes underneath cover to the north. And we have a beautiful diabase target here that hasn't been drilled yet. So that's something to think about. And then it forks off in 2 other directions. There could be diabase targets out here, but on a volume basis, I like this one. And I also like it because of the structural setting up here associated with a ray shear zone. Lots of places of depressurization along that thing. Okay. Looking at the Biotite hornblende granodiorite, that's our 2.75. There's actually a lot of more pulsing, so there's more phases in this. Pluton's quite complex. And then the Biotite granodiorite stage 3. That's the guy spatially you want to track. You'll find your good copper mineralization associated with that. Next, this gives you an idea of that. This is a K-feldspar vein associated with a little bit of chalcopyrite quartz, be your so-called D veins. And you can see it's cutting a stage 3 biotite granodiorite, which in turn cuts a biotite hornblende granodiorite, fairly mafic, which has propylitic alteration and pyrite veinlets that are cut by this guy. So the main best takeaway here is that this is not all about one Pluton source and one fluid release that does a classical Lowell Gilbert light bulb one-shot zoning system. These are a sequence of Plutons, each with its own fluid release event. And that's what I think new explorationists need to take into account. And I think if they start thinking along that line, that's going to improve their exploration success. Next. So in summary, we have reorganization events between mountain building episodes that allow oxidation of sulfides into collectible and very economic chalcocite blankets, for example, mineral accumulations. Arizona needs to geology needs to really look at the influence of flat subduction. It's underrated. And how that we've built our crust from the bottom, not just by accretion events, but that's been caused by flat slabs just slapping up and accreting to the base of the evolving Proterozoic crust. And then flat subduction is the melting. When that happens, you melt that crust and you make peraluminous granites. And that's something that current tectonics has not taken into account. Supersystems are important because they're essentially a large batholith area that's fractionating smaller repetitions of itself into the upper crust, and so you create several clusters of mineral systems like that one we saw in western Arizona. Jurassic guy. Again, don't get too because we've had so many of these different events, they're an opportunity not just for copper, but I would again stress gold. But if zinc's not that bad lately and silver's not that bad, you want to maximize the opportunities for that. You want to be looking in the alkali calcics, and you don't want to be looking so much in the calx. Don't chase. That just restates what I just said. And again, flipping that little coin a little bit, alkali calcic mineral systems are sucker plays for copper and or gold, unless you want that zinc silver. And with that, we wrap it up. We've done 4. We plan a webinar where we're going to talk about the other ones and expand and talk about the whole thing over a 2-hour short course, which we'll be announcing through our website for in the near future. And now we can take questions.
Yes, we'd love to open it up to discussions. Again, just speaking about the
I
webinars.
saw Conway was trying to sneak one in.
You have a couple of chat questions. You see them down there?
Let's stop sharing for a second. Let's go to chat. Okay.
Oh, there's Sandy Powers.
Where does Baghdad copper fit into the system, Stan?
Metaluminous calcalcalic oxidized. Hydrous plutons.
Ed Madsen
Stage
has a question.
Stage 3.
Stage 3.
And there might be another stage 3 to the southwest, but I think pretty much the way that one's set up with a sort of star-shaped thing where there's 2 things converging from the northeast and the southwest, and those are stage 2s. They fractionate to stage 3 at Baghdad. Then there's a major tectonic shift to northwest trending fractures, and stage 4 goes into that. So Hillside Mine to the north is a stage 4 lead zinc play.
Okay. Ed Madsen, your mic is unmuted.
Okay, I would like to know, when is the 2-hour course? Is it going to be through Tucson German Mineral Society or AGS?
No, this will be through the Research Institute. So we have a website, magmachemri.org, and we will certainly share it with all our social media and get it out there through any form possible. But it's, it'll be available through the website.
Can you give me that website name again?
Yes, magmachemri.org. And I can share my screen. This is the home page of the website that we're looking at here under courses. That's where you find our 2020 webinar that was about the oil and gas industry. Next, we're doing a webinar series on the Magma Metal Series and metals exploration in Western United States. And so the webinars page will have down here as we're loading, Sandra Powers raising her hand. Yes, Sandra.
Can you hear me?
Yes.
Stan, I was wondering if you had a bubble diagram for the PC.
No, but I know, they because they're peraluminous, they start out at 65% silica. So you start out fairly evolved in a stage 3 type system, and then you move into a stage 4. Basically, the stage 3 is a biotite granodiorite, peraluminous biotite granodiorite, and then it evolves into a stage 4, commonly soda aplogranite. There'll be a lot of aplite associated with that. Highly differentiated.
So you think they're maybe kind of more telescoped than the other ones that have?
Yeah. The stage 4s typically are a lot veinier, more telescoped, but have a little high grade gold. And what happens with that is things like Vulture would be an example of that. Gold Basin would be and a lot of the mines that were mined historically for tuna were mining these highly evolved stage 4s. And what's interesting about that is if you back those down into the stage 3, the large tonnage Herraduras of the world are probably associated with lesser differentiated stage 3s where you get more pluton hosting. And the Chief Pluton, for example, at Mesquite, it hosts a lot of bulk, lower grade gold mineralization, but it's cut by stage 4 too. So.
Okay, thanks. Good to see you.
Yeah, good to see you. And I need to do a fractionation chart for those peraluminous guys. just not enough time of the day. This guy by the name of Troy has occupied my time. He wants to know everything. Any other questions?
Yeah,
I know
There's
Conway had one, but he tried.
Well, there's
to
some things in the
interject.
chat box, and you might want to go there and see.
All right, I'm starting at the top. That's all private stuff that I was dealing with earlier. Does melt
there he is.
composition and thus potential mineral product vary as a function of percent melt?
Well, you saw sort of a synthesis of that going on with the bubble diagram. So once you know what series you're in after specifying aluminum content, alkalinity, water content, oxidation state, and halogen, that gives you the series. And then as a function of fractionation of within a magma series, you produce those bubble charts. And magma, you definitely want to be aware of magma volume, because the higher the volume, the higher the hydrothermal volume fractionates are.
What would be the chance of a deep tin tungsten deposit at depth beneath an alkali calcic lead zinc district?
You can have them. There is tungsten associated with alkali calcics. And the other thing is that one of the things that wasn't talked about here is that in the alkali calcics, you have tin and tungsten, and that's associated with reduced formats. So we're talking about the Bolivian tin tungsten province, for example. And that will have high level silver veins, epithermal silver veins, et cetera. So in the case of Bolivia, that's a classic physical connection between high level sort of epithermal and almost xenothermal silver polymetallics and then deeper tungsten.
Daniel Koenig says, "Hi, Stan. Would you say that the composition of the previous orogenic events affect the oxidation of later magmatic events, or does it affect the fluid exsolved of those systems?"
Interesting question. What we found over, basically we've done a lot of ferric-ferrous ratios studies of Arizona, and what we'll do is one fun thing that we do is go to a Precambrian road cut that's cut by laramide plutons, or sometimes 2 or 3 generations. And what we find is that the ferric-ferrous ratios tend to be the same. So once you start out, and it's sort of a mass balance thing, because Precambrian crust oxidation state has a lot more mass than an incoming, say, laramide pluton, unless it's a peraluminous batholith. And so it will buffer the oxidation state towards the mass of the pre-existing rock. Now, you can change the oxidation state structure of the crust too. So, for example, when you had a relatively oxidized crust in western Arizona from the Jurassic to the laramide, but when the flat subduction came through and you brought in the orocopious schist, that's a very reduced rock. Part of that is indicated by graphite, but also extremely low 0.1 to 0.3 ferric-ferrous ratios. And any plutons that come into that or are fractionated from that, it's like peraluminous granites, like we have one up in western Arizona near Parker. They're the same oxidation state as the orocopious schist, but that sits beneath these big flat faults, and you cross over that and you all of a sudden get very oxidized, which is reflecting the oxidation state of the crust that predated the flat subduction. So you have to be careful with that stuff.
So Michael Cook has a question, and I believe it's in context with what you were talking about at Troy Ranch. It's a prospect that you have and we're working on, and you have some drill holes suggested. He says, what is the range in
1,000
depth?
feet.
1,000-foot drill holes.
Yeah, should catch most of it. Maybe 1,500 for our donut target. Just give us a phone call. We'll fill you in with more stuff. We got several people looking at it right now, but nobody's signed any real deals with us yet. So got some CAs out there.
Yep. Huh.
It's a good play because it's got diabase. And I can't wait to see if that. And I know it peeks out from under the Troy quartzite on the right next to the stage 3, and it's crawling with copper right there. So I want to chase it under the Troy quartzite and see, because it's a big sill in the Troy quartzite, probably 1,000 feet thick.
So a question I have, just because I've worked with you guys over the past couple of weeks, putting this presentation together. Obviously, we're doing the more detailed webinar, so maybe we'll get into the weeds on this then. But you did the whole state of Arizona. It's, what did you say, 1,100 polygons?
Yeah.
1,100 different mineral
Well,
systems.
Jan says if you take it out, it's 983 or something.
Oh, that's right.
No, 930 mineral districts, but with all the sub-districts and the super systems, then it's closer to 1,100.
Okay. And now talking about being in the rock system, being in, you're in an MCA, you're calc-alkalic, you're in the yellow, you have potential for porphyry copper statistically, but you need to figure out, are you in stage 3, stage 2, stage 1, stage 4? In the whole map, how much of that have you done, and how many more do you need to get done?
You've just seen the top of our iceberg, buddy. Back in the day, we did a lot of whole rock chemistry for a lot of the mining companies. We have a huge database on the subject. So we focused on the laramide porphyries, obviously. And so we kind of pretty much know, we've matched up the petrochemistry with metallic metal expressions in the alteration assemblages. So we've got a pretty good handle on that. I mean, it's repeated. That bubble diagram is probably repeated with petrochemistry and mineralogical description over about 30 case histories.
Wow.
And we don't see very much exception to that. So,
but for example, Yuma King is a copper prospect. It's
got two main stages there that are productive. One is the stage 3. Actually, we've got 4. There's magnetite skarns associated with Hornblende monzodiorites with minor copper.
Now you're in a quartz-alkalic system. You're
Correct.
in a pink polygon, and within that pink polygon,
weakly oxidized to oxidized in terms of ferric-ferrous ratios. Magnetite stable.
Okay.
And what it's done is so you've got magnetite skarns with minor copper associated with actinolite. And we've got magnetites, andradite garnet skarns associated, that's our good guy, associated with a stage 3 biotite quartz monzonites. And then this, I'm just summarizing it. And then we've got a stage 4 alaskite plutons, aplytic alaskites, associated with a molybdenum mineralization with minor copper.
So you have
their sequence quite similar to the one at Bingham.
You have 5 metaluminous systems, and you have 5 peraluminous, or how's the system level? How many different systems are there in the magma metal series? 10 systems.
Well, there's 2 mega series guys. That's the peraluminous, metaluminous, and then when you split them by alkalinity, that goes up to about 4 for the peraluminous and 10 for the metaluminous.
So you got 14 there, and then you got 5 stages per each of the 14.
No, it can be anywhere from 1 to 5 stages typically.
Wow.
Although Troy's a bit of an exception because it just sort of burped along.
Oh, yeah. You talk about stage 2.75.
Right.
I've
got about 7 or 8 of them there.
Whoa. There's a bunch of other questions in the chat that look really interesting.
I'm so sorry.
David asked how much post-ore extension is present in the Globe Miami area.
Well, I obviously have a difference of opinion with some of the conventional wisdoms out there. And I think that the Schultz granite is it's a really good stage 4, and it's got its own stage 4 mineralization associated with it, which is like the Bronx tungsten veins, tungsten moly veins, the American Peak moly veins, and then there's some arsenic copper veins over there at Gibson. And that thing is its own fluid release system. It's not the core of the main district. The other districts are associated with stage 3 biotite, granodiorite, porphyries, and they're their own cells. They haven't been sliced off the top. I think there is some extension associated with the post Big Dome equivalent faults that basically rim the globe basin that go around from the North Pinal Mountains all the way around the rim up to past Miami. Sort of a U-shaped pattern, but I would say most of that's basin and range. I think a lot of the blocks that are up there, for example, the Pinal schist breccias that are over there near south of Pinto Valley, are landslide blocks that have come out into the gravel deposits. So they're distension or just landslide, and they're not part of any regional extension. And I'm just not a fan of that at all regionally.
Mike Doe says, what are your thoughts about the 1720?
Yeah, the one that showed up with some dates on it.
Just west.
That was a pleasant surprise. Yeah, that's sitting in the nice little Precambrian porphyry copper moly system. So ontogeny repeats phylogeny there in the Cherry Creek batholith, which is a little bit more oxidized at its southern end, and it fractionated the Squaw Peak thing. I don't think it's very big, but I think it's a fascinating little porphyry because it's just like the ones we've got now, except it's 1720, or actually I think the dates are closer to 1730. You look at Silito stuff.
Okay.
A little note on that in economic geology.
So we're going to jump back in the presentation for this last question on the list so far. In terms of the ferric-ferrous ratio, pull the map up, which has got a big question. What was the significance of the northeast trend of less oxidized material? Was it lithology controlled? Oh man, we're talking redistribution of electrons in the mid-crust now, Stan. This is getting good.
Oh, quiet.
Okay, let's get back to the ferric-ferrous ratio.
Well, we need to look at the map.
Yeah,
I
right
can
here.
talk to it a little bit better.
Okay, this trend right here.
What we're not showing on this map is all the sample points. We have several hundred ferric-ferrous points that constrain those, although in some cases there's areas of no data. In other cases we just don't have the data on Pluton X. But what we've also done is we've taken mineral systems where we know the oxidation states, and then we find one where we have the mineral assemblages that give us the oxidation state of the indicated by the mineral system. So we use those. And for example, if we see oil deposits, we automatically know that we're basically at 0.3 or less. So that's what that big northeaster is up there. You got Dinibikea. You just had your hand on Dinibikea, which is a well-known Manette-related oil deposit, which is fascinating in itself because it's only hosted in the Manette and not the porous sandstones. So how the hell did that oil get into that Manette? It didn't migrate there. I think it formed with the Manette. Man, and that gets back to some of our ultra-deep hydrocarbon arguments. Yeah.
Last year's webinar series.
Yeah.
This goes into the Paradox Basin right here, huh?
That's a little bit of paradox slicing in there, yep.
So what controls the shape?
Well, there's it's picking up some, put your cursor right there. That's about where the Payson is. And there's a ophiolite at Payson. There's some highly reduced basement there. There's also the Green Valley Pluton, Gibson Pluton complex, which is a part of the Green Valley Gold District, if you look at our maps. And there's also, keep bringing your hand down here. That's the Mazotzels. That's the Mercury districts. Those are typically highly reduced where we have control on them elsewhere. And then the Phoenix Mountain mercury districts are over in here. And then they end at the Sierra Estrella, which is here. That's more oxidized stuff. But we're using the mercury as a low oxidation state indicator. So we use sort of a panoply, if you will, a collage of things that indicate oxidation state other than just ferric-ferrous ratio. But this is, if we've got one of these, that's our hard stuff. But within the plutons themselves, if you've got a magnetite sphene pluton, that's going to give you probably a ferric-ferrous ratio within this range right here. If you have magnetite only, then that's more oxidized. If you have hematite, magmatic hematite, that's going to be up in here. If you have ilmenite, this is the classic ilmenite-magnetite series distinction of Ishihara. That usually is going to have a ferric-ferrous ratio of less than 0.6, and basically a lot of gold deposits are associated with plutons that are reduced. So if we see a gold deposit where we know it's mineral assemblages and its affinity, but we don't have a ferric-ferrous ratio, we'll make a reasonable assumption about that, and we have some of that going on over in the, because it's controlling this contouring over here.
Wow. Okay. We got a big one here. This is from John Mark Stouty himself.
Oh, John Mark.
The man, the myth, the legend.
Go
Stan.
back to Vancouver.
Propylitic halo, green rock halo. Can you use this to tell fertility for a stage 3 MCA 14 porphyry copper?
14?
SEG 2020 published a special volume with 8 articles, all describing the epidote. Chlorite, microbe, what am I looking at? Micro.
And using this to vector the ore bodies.
Yep. Such as, what does that say? Uena?
Yeah, these are chili.
Bring John Mark in to read this. Do you think this approach is valid, and what concerns, if any, should one have in using this green rock approach? How distinguish from stage 2 event in a microprobes and vectoring? Thanks, Stan and Jan. Great presentation, John Mark. Agreed, John Mark. Sorry, I kind of butchered that.
All right, John Mark. That big shit-eating grin of yours. Okay, so you're well aware of some of the early work we did on propylitic halos and the idea of, can we use things like rare earths and other elements to vector from the halo to the porphyry copper center. And the problem with that is that we found that things like epidote chlorite, which are the main constituents of the propylitic halo, were associated with more mafic plutons in the sequence, diorites, and that those were intruded by more evolved plutons, which were then in turn cut by the more potassic and familiar alterations that you see with the cores of the porphyry coppers. So I would be a bit skeptical. I think some of that they're would be talking about, if you looked at the data carefully, I think it would be coincidental. Because they're assuming the light bulb model, and they're not assuming looking at the paragenesis of the plutonic sequence. And when you start looking at that, that's when you start seeing all these cross-cutting relationships. And a really good place to see that, you don't need to talk to me, just go to Carton's work in the Yarrington district. And that's where he started seeing the McLeod Hill Monza diorite, which is associated with the soda calcic and epidote chlorite alteration, and it's clearly cut by the bare quartz monzonite, which is then in turn cross-cut by the potassic porphyry copper related mineralization. So that was a big red flag. And then I started looking for that. I saw it at Baghdad. I saw it in case history after case history. Wow. Is that once you plug, as we were showing in that Troy thing, once you plug the Pluton story into it, you come up with a much different thing. So I would be a little skeptical about that.
John Mark's giving the thumbs up.
Okay.
Right on. Ron Luthi says, talk to him about Diamond Joe Peak.
Alkali calcic high risk. And I'm a little bit worried about Tim Marsh's Kaba play up there near Kingman, because they put a drill hole into something that was the dominant sulfide was sphalerite. And then they tried to argue that, well, that's on the edge of the porphyry system. And I'm going, well, yeah, but it might be fundamentally, might have fundamentally hit spit zinc. But I don't know. We need, you need some dates on that thing. You need some whole rock chemistry. There's plenty of ways. That's what this thing is. It's very testable. So you can go get the data and you can figure out where you are in this model and make predictions. What people are doing is pulling the trigger on with much less data that doesn't allow them to make an informed decision. Oh, what do we want to pay money for a whole rock analysis for?
Science budget. Got no money.
Yeah,
for that.
exactly. I got copper, man. I'm getting my drill rig out here.
Geology is back, folks. No question about it.
And I've done the same thing in the gold business. That's got me into all kinds of hot water. Sandy Powers knows all about that. With FMC.
We got, please keep the Arizona section AIPG in the loop.
I sure do.
She agrees. But she actually likes this stuff. That's why she keeps showing up. Now I'm going to have a whole herd coming after me.
Stan. Thank you, Stan.
Mm-hmm. You're welcome.
Stan, this is Dave Knight.
Uh-oh.
Yeah.
You know, hey, where does the IOCG
blacked out like I was, and then he.
Where does the IOCG systems fit into your? Yeah.
Most of them are quartz alkalic. Roxby Downs is quartz alkalic. Peraluminous quartz alkalic. High fluorine.
So is that the same stuff down there by quartzite? Does it still fit?
IOCG, again, that's another classic model argument. We
can go into the details in the webinar on that, but back to your point about quartz alkalic.
Iron oxide, copper, gold, but
right.
What you got to be really careful of, and a lot of mistakes have been made on this model in Chile, where they get into the flat segment magnetite belt, places like Romerol, and those are really calcic, oxidized iron things that have a little bit of copper, and people have tried to play those into the Olympic dams of the world, and they have had no success. And what you do is you stack up a few parameters that are consistent with somebody's literature model, and off to the races. And because it's in economic geology, it has an authority, so you can easily go get money with it. But you've got to do a little bit more homework and a little bit more filtering. And I did a lot of that for IOCGs in central Chile. We just didn't have anything that stacked up with the Australian stuff. But and there's a lot more to that than I've just said.
Yeah, we're going into that in the webinar for sure, because it's a very interesting topic.
Yeah. Oh yeah.
When is that webinar going to be?
Next Thursday.
Wait a minute. Have you already got a date for this thing?
You told me.
I did not.
You said let's do it Thursday.
I did not.
Well, you forgot. You told me. Yeah, next Thursday is the plan. We were doing our webinars.
He's killing me.
Last year.
I'm too old for this.
Well, it worked out great because we said, hey, we got an AGS talk we need to prepare for. And Stan sends us a 175 slide deck and says, I'm ready. And we go, let's trim this down a little bit.
I didn't send you 175 slides.
Well, but what it did was it allowed us to come up with several very interesting topics that really dropped out from this. We crunched it down into 45 minutes, and then we made the decision that we need to do an extended AGS presentation. Jan and Stan's work on the Magma Metal series in the state of Arizona. That's really our focus for the Research Institute for 2021. We did oil and gas last year, and that's fascinating stuff. But 2021 is going to be all about Arizona, the parade of orogenies, the magma metal series, all this work on the state. We'll do virtual field trips to some of these places that have amazing outcrops that he made these discoveries in. And we'll even bring the lizard. I don't know how we're going to do it.
Oh, that's what you're going to do. That's how you're going to get me. Oh, you take the lizard.
So now that you're on the spot with this, Stan, last year we did our webinars around 10 in the morning, 10 to noon, Thursdays. Does that work?
Oh, now you want a time.
How do you feel about that? 10 a.m.? Right after the breakfast burrito?
Get out of here. I suppose.
10 a.m. next Thursday, Ed.
And the website?
magmachemri.org.
Okay.
And go to the webinars tab, and it'll have the link right there. Webinars tab, you click that, it'll say join webinar here, and you're just like this meeting, you'll be in.
Uh-oh.
Thank you.
Yes, sir. Thank you.
Do you save them so you can watch them later or anything like that?
Yep. So that's the beauty of being a registered member of the website. It's free. You just click the register tab and give us your email information so we can keep you informed on all this stuff. In exchange for your contact information, it's free. So we have over 12 hours of the webinars we did last year, over 500 pages of publications and resources, the PowerPoint presentation for each of the webinars, completely downloadable, YouTube, to watch the webinars at any time on your leisure, on your schedule. That's exactly what we've built for the website. Yeah.
Great.
More to the point, Troy has built it. I've just talked. Although I do build a lot of the PowerPoints.
You built the whole thing, Stan. You and Jan built this all. I just came in and said, hey, I think we could set up cameras and talk about this.
We can go virtual.
Yeah.
Oh, Bill Bessie's out there. How many people we got that showed up at this thing anyway?
Stan, you had about 94, 95 people at the top of the hour. Are we winding? Do you want to wind it down, Stan? We don't want to hold you any longer. We know that you need a beer. So
I need a beer, and I have to get ready for this guy who's already slotted me in for next Thursday. Give me a
Stan, question. This is Mike Doe.
Mike Doe.
Yeah, Mike.
I got a question for you. As you know, I work in the Proterozoic a bit, and
I know you. Yeah.
1982, Titley had pointed out, I think other people have pointed out, there's a trend that goes kind of northeast across the state at about Globe, Miami,
right,
running that area. And it's sort of a boundary in the Proterozoic that separates the Pinal schist, or what they call Pinal schist, which we know is really much more complex.
Yeah, you do, especially from all your work north of Globe.
Yeah, versus what is more like Mosasol terrain. And I'm kind of thinking that it's something of a very fundamental crustal boundary in the Proterozoic. And I've often wondered if it isn't in part what has kind of rheologically controlled the nature and the style of laramide thrusting, basically from the south to the north, there's certainly a difference in terms of how far east or northeast the thrusting goes in the laramide, certainly farther to the east and to the south of the trend. Anyhow, I was wondering if you had any thoughts about that, whether or not that's a fundamental crustal boundary could be concentrating or controlling some of the much later deposits.
Well, I'll throw one observation into that, and we can talk a lot more than it's just this observation. But were you around here earlier and saw the oxidation state map?
Yeah.
What's the oxidation state map? Okay, so we see this big northeast trending thing, and it comes right on down through the mass itself. So it in part coincides with what you're talking about.
Yeah, we call that that would be kind of along the Slate Creek, Moore Gulch trend. It's kind of wide.
Right.
The one I'm thinking about is more like what we call the Holbrook trend. I call it the Globe Superior trend because it's just sort of a gray area. In fact, even at Buffalo Hill, the Troy quartzite's got this massive conglomerate, and it suggests that it's a long-lived structure to me. That probably initiated in 1708 during extension, which I think formed a lot of the northeast trends across the state prior to the last phase of the Yavapai deformation, which in my mind ended about 1670. But then those trends were reactivated. They were probably reactivated, at least in the Troy quartzite time. That's what gives us boulder.
Yeah, what we like there is we're impressed with some of the Peraluminous plutons that are around 1700 to 1690.
Yeah.
And for example, the Bradshaw Mountains batholith or Crazy Basin batholith.
Yeah.
We think there was a period of flat subduction, and that's sort of also the southeast limit of what we call Yavapai.
Should I pull up the Yavapai?
Yeah, you can do that.
Because we know we have Yavapai age rocks underneath the Mosasol Mountains. That's the
right.
Ophiolite. You've got your alder series.
The Pacen-ophiolite, yeah.
Yeah.
That's about as far east southeast as Yavapai orogeny ages get, though. Well, no, you get over into the Red Pan area and all that stuff. What are you doing?
This is all Yavapai aged magma metal series calls.
Yeah, you can see that southerly, kind of a northeasterly trend along your southern boundary of most of those.
Yeah, that's a little massive sulfide trend.
Yeah.
And these are the Mazatel mercury districts.
Right.
Thought it would help better, but maybe not.
But yeah, there's definitely some kind of a suturing going in there, and all of that roughly ties into this oxidation state thing we're talking about.
Yeah. But see, that's to me is separate from what I see on the globe superior trend. I'm more, it stands out to me along that globe superior trend. It's more of a difference in the laramide deformation. To the north, you just don't see laramide deformation across that boundary, but to the south, it seems to extend quite a ways up. And in fact, I would even argue in the Upper Salt River Canyon, there's a little bit of evidence of shortening perhaps laramide shortening that overprints some of the Proterozoic deformation that's in the area. That's like a Quartzite Falls area, Clay Spring.
Yeah, I'm not familiar with that.
It's Stan, it's Monty. I chime in here because I think he's describing the Gila slab tear because it's two totally different provinces, the north and south, I mean, especially in the laramide. Right?
Yeah. Yeah, well, that's this thing.
This guy?
Yeah.
So the slab to the north is flatter. The slab to the south slab to the south is flatter.
This is also known as the Jemez line of Mayo.
Yeah,
Right.
they call that the Jemez line. It depends on who's interpreting it, but I've seen it go a little bit to the north as well, a little bit further north. But it's hard to say on this. But.
Well, it's not a single line. It's a tear in the subducting slab because you're subducting two ages of crust because you're subducting a fracture zone. So what happens is you have a scissors fault and you have hundreds of miles of movement on that scissors fault the further you go east. So it's not the line is not knife edge, but they seem to be staying in the same place since the Paleozoic, these slab tears. But there's huge differences in uplift across that slab segment. And
that would sort of more or less go like this. It's a little
more easterly.
Yeah, it's
more
like that.
Yeah, I mean, you have a series of volcanics that continue up by Snowflake and or so, in those areas. So that's all not what I call kind of the Holbrook or the globe superior trend. Anyhow, I just wondered what your thoughts were on that. If that's because of the downgoing slab, or is that maybe a
well? No, I mean Marty's right. I mean there's definitely a slab tear story, and that shows up starting certainly by the end of the Paleozoic. We see its influence.
Yeah,
but it may influence. It depends on how you want to play the Permian magmatism game. Not a lot of good data points on that. But yeah, slab tears are, and they actually propagate and influence their way up into the upper crust as well. So you just see different topographic elevations on either sides of them, et cetera. They show up in the radar imagery, et cetera. So
yeah, we sort of think of there's even potential slab tears even in the Proterozoic that we've been debating.
Absolutely. And one of the things that we're going to do, we've just managed to assemble this data. These are relatively well-constrained data points as far as their geography, but we've yet to look at really gory detail as to how they relate to each other. For example, if you look at the massive sulfide distributions, you'll see that what's metaluminous calcic for us is superimposed on a metaluminous calc-alkalic. So the Iron King Spud Mountain Volcanics appears to be a little bit older, around 1750, where now that they've got a proper date on Jerome, that's around 1730. And that whole belt's probably 1730, close to it. But then you have going down into the Phoenix Mountain, Mazatzal, Mercury systems. They're not well dated, but the best guess is that they're around 1720. 1730. So there appears to be a southward migration of some of the magmatism that's of Yavapai age, and it suggests flattening coming from the northwest. But then what happens is that all the other orogenies, Picarus, what's left of Mazatzal, because Mazatzal's, a lot of that's being shown to be Picarus age stuff. But all of that is interacting along that line that you're talking about. And the subduction zones appear to flip. So they flip from subducting to the southeast during the Yavapai. That's what we think we see. And then the polarities switch to where they subduct to the northwest, coming from in Mazatzal. And it's certainly by Picarus time they're doing that.
Right, a Picarus time for sure. And it seems to be dampened, the northwest shortening, what I call the Mazatzal Picarus orogeny.
Right.
It seems to get dampened by this massive pluton, the Rune granite, Oracle granite, the El Oso, right around 1450.
Yeah. Now, do you think those things post-date those big, beautiful folds in the north end of the Mazatzals?
I think they come in late.
Yeah, that's what my guess is. But so yeah, the folding would be, and that's northwest directed folding.
Yeah. And I think what it does, somehow it's so massive that it literally dampened the stress field, because Niemeyer and others, 94, say they've got shear zones that are active in the supposedly anorogenic granites.
They're not anorogenic. That Monty and I will get right after you on that one.
The thing is, they're so large that in a lot of areas, you just don't have a syntectonic fabric that's super clear or even evident.
Exactly right. But they're also, a lot of them are peraluminous. Oracle granite is peraluminous, for example.
And a lot of them have flow strain within them. They're not just brittle. In fact, the whole peraluminous system start out as ductile and they end up as brittle. There's a whole progression as they evolve. Another thing, Stan, you should talk a little bit about Greisen mineralization with these peraluminous calcic gold systems, and that these things are deposited at 8 kilometers. I mean, we kind of missed that point. That's a pretty major point.
Yeah, we only covered 1.8 billion years in 15,000 magma series. But yeah, so if everybody out there has got their favorite things that I didn't quite talk enough about or missed it. But yeah, like Mike Doe, there's a lot of stuff he's talking about that's really important to this whole story. But I'm curious, because these big plutons are picking up the flat subduction event. And again, I think that's something that has to be played out through the Proterozoic, because a lot of the interpretation of the Proterozoic orogenies is accretional, where you just bring in an island arc and stick it onto the edge of a growing proto-Laurentia. But what we seem to be seeing is there's a lot of flat subduction that's bringing things underneath all of this stuff. So, for example, in the Picarus orogeny is a huge thing. Well, it is the 1400 granite event. The 1400 granites are just big, and many of them are peraluminous. We've got, for example, in the laramide, we have huge peraluminous plutons, like the Gunnery Range batholith. That's bigger than the Oracle granite outcrops, Oracle plus ruin. So huge amounts of these silicic sialic magmatism came in during the late laramide.
Wow.
And that's a model for what's going on in the Proterozoic. So you got to look at ruin. And Picarus has a huge amount of magma volume, but they're not anorogenic. I think
one thing that Chris Daniel shows is in the Pickery Mountains in New Mexico. He shows a temperature and barometry that indicates in 10 million years, rocks went really deep, really fast, and then they came rocketing back up.
That's right.
So there's quite a bit of dynamic tectonism going on, and the shallow slab makes sense with the granites, and again, forming ductily initially and then into a brittle stage later is consistent with this rapid uplift as well.
Yeah, and you form a huge peneplain erosion surface under the Apache group.
Yeah, Apache group. My guess is the Apache starts sometime around 1320, 1330.
That's right. Yeah, based on that tough date in the Dripping Spring. Yeah.
Yeah.
And another little detail: you don't get volcanics over peraluminous system. I mean, I don't think they fundamentally understand peraluminous. I mean, they're extremely hydrous up to 10 volume % water, and they don't make it to the surface. They crystallize at 8, 12 kilometers, and that's where you see the gold deposits deposited. But you have such high fluid pressure, you can actually get open spaces. And anyway.
Yeah, well, we say that in our abstract. Good. And the Eocene erosion surface is the laramide equivalent of that erosion surface under the Apache group. It's huge peneplain. So basically I think the flat subduction creates these huge areas of epyric uplift, and it happens fast. In the laramide, it all happened, this whole thing goes down within about 10 million years, just like they're talking about in the Picarus stuff.
Wow.
So, yeah. So once you make this peraluminous, metaluminous distinction, just that alone gives you a thought process to attack the regional tectonics. That's a huge distinction. But it's not being made because of the IUGS double ternary triangle. They've trivialized what granites are on that diagram.
So Stan, can I say one more thing?
Now,
the panel of crust above these slab segments between the slab tears, it's a unique geologic province. So when you go across that Gila tear north of right at Globe, that's another geologic province, and all the timing of all the geology is different. In the laramide, it's off 10 million years? The one from the north.
Yeah, there's an offset of the laramide arcs. There's segmentation going on. Yeah. Yeah, that's all really important. But from what Jan and I are coming from, that's all secondary to just getting the basics of the classification down, and then you can go. And once you then start looking at the geography of all that, then what you're talking about comes into play.
Right.
Which is important.
Well, yeah.
But the most important thing is just to get the basic petrology classification right.
How's the dotted line drawn? How did you guys come up with that on the Cracks of the World map?
Good.
How do you create that dotted line? And how do you confirm exactly where it is when your boots are on the ground?
What are you laughing about, Lonnie?
There's only one way. I've tried everything, but there's only one way. Stan knows that.
You have to assemble all the petrochemistry and look at it in terms of time slices, and then you'll start seeing the offset of these petrochemical belts.
It's a chemical facies of the arc, the alkali, calcic, calc-alkaline. So those are chemical facies of the arc, and you can geographically plot those on a map as a time slice. And then you'll just show right up because there'll be a major offset in those facies of the chemistry. And that's the only way to actually really locate those. You could see them in the topography and the morphology and, patterns of igneous rocks and mineral deposits. But the only way to really do it is the chemical facies of the arc in time slices. It's basically what you're doing is drawing a contour map of the subducting slabs in that time slice. So you can see that, the one is flatter and one is steeper. It's just simple. But that's the only way.
I'm pulling up the website because I'm remembering an image. Is it something you're talking about? Something along the lines of this map?
Yep, that's it. Yeah, that's it.
Blow it up.
Chemical facies of the arc, and the orange is deeper. Then the blue is the flat subduction, and then you get the calc-alkaline, the alkali calcic, quartz-alkaline. So that's a contour map of the subducting slab in that specific time slice. And each one of those slab segments, the crust is a geologic province. It has its own timing, own characteristics, its own characteristic of melting, because that slab brings down different amounts of water, and it hydrates the mantle wedge above it in different ways. So you can have metal-genetic provinces that are limited to those specific ones, like porphyry copper province. Porphyry copper clusters in one slab segment.
So that's what those dotted lines are.
Mm-hmm.
That's a very crude representation. We have much more resolved. We have multiple time slices for the Western
Yeah, but
US.
the point is that it does correlate with what Doe sort of was talking about. And so there may be some Precambrian ancestry to these things. Yeah, and that's another extremely important point that you forgot to mention, Monty.
Maybe I haven't. Maybe I'm not.
Hey, Stan, Stan Mike Conway here. We're running out of time. We slotted I think till 8:15 or 8:30 for the presentation and the questions and answer period, and you're all going to disappear in a moment or two. So
okay, but I want to just make one final point to expand on what Monty was talking about, and that a lot of this stuff is from our Cracks of the World. So pull the Cracks of the World thing up.
Okay, while I pull it up, tell everybody thank you or something here.
Well, thank you for coming, but you guys already know that.
And reach out anytime if we can do anything for you.
To be continued next week. So these are Cracks of the World, but the point is that note that how we link the cracks to the oceanic fracture system. And a lot of people that built the oceanic fracture system come to the edge of the continents. Continents are just blank slates. And what we found is that these things go through the continents, out the other side, and connect into the crack system in the opposite basin. In fact, they can almost go all the way around the planet.
That one does.
Yeah, and this is our tectonic equator. But the point is that the oceanic fractures get started because this is all young post-Paleozoic oceanic lithosphere, mostly post-Jurassic. And whereas all of these, as Monty has developed at Stockton Pass in his thesis, these things started out in the Precambrian. So basically the Precambrian architecture of the continents is controlling how the ocean basins open up and how the fracture systems in those develop. So the Texas zone, for example, is controlling how the Murray develops.
Wow.
And then you've got the Clarion tied into the Mexico shared system, et cetera. But then this goes all the way through Cuba and then out into these big cracks systems in the Atlantic. And then there's this thing going on in Africa that we see in the magnetic gravity data. And again, that thing I think is controlling how that, and then that links through at Laurentia and then all the way out. So basically the fracture systems in the ocean basins are controlled by what's, I think, is going on in the continents. And I think the Precambrian architecture has a big vote in all of that, and where slab tears develop, et cetera. Wow. And with that, go to sleep.
Hope to see you all.
Happy dreams.
Next Thursday, hope to see you there. We'll go into the details of this, and we'll have some more fun and the deep dive. So we'll see you there.
No, what I was going to say was, if you want, we can stay on. People can just unmute themselves. We can kind of have a follow-up happy hour if people are interested.
Yeah, I need a beer.
Got to run to the Dollar General for Stan.
Thank you very much to both Stan and Jan. That was a great talk and really appreciate it. And definitely let us know, Troy, on a link to the webinar next week, and we can try to get that up on our own website as well. It sounds really fascinating.
Gosh, thank you so much for that. Yeah, we will, certainly.
Well, great. Yeah, thank you both. And I guess stay on if you want to. I got to go grab something to eat. So I'll kind of listen in as well, but I'll turn my video off and mute myself. But thank you, and Happy New Year to everybody.